Buoyant forces and Archimedes principle. When we have an object that is immersed inside a fluid, it's going to feel an upward force which is applied by the fluid. That's called the buoyant force. The upward force exerted by a fluid on any immersed object. So why do we have a buoyant force? Well, that's basically due to the pressure differential between the top and bottom surfaces of the object. So that comes from the variation of pressure with depth in the fluid. So we can say that for the top surface of the object, we will have a pressure exerted perpendicular to the top surface, which is the pressure at the top times the area A. And then we have the bottom pressure, P bottom multiplied by A, which is in the upward direction. And then we also have the weight of this object, gravitational force, that is pointing down, mg. And let's say that the height of the object is h. So the magnitude of the buoyant force on an object is equal to the weight of the fluid displaced by the object. That's Archimedes' principle, and let's see how that works. So for this cube that is immersed in the fluid, if we write the net force on the y-axis, so this is our y-axis, P bottom times A is pointing up, P top times A is pointing down, and gravitational force is pointing down. And this basically pressure difference times the area A is called our buoyant force. So we have P top times A plus rho fluid GH times A minus P top times A is equal to the buoyant force. Why is that? Well, this part, the pressure at the top plus rho fluid GH is the pressure at the bottom. So remember that the pressure varies with depth, and it's the pressure at the top surface plus rho GH, rho fluid GH, that's the P bottom times A. So we have P bottom times A minus P top times A is equal to the buoyant force. And because P top times A's disappear, we see that the buoyant force is density of the fluid, gravitational acceleration G, H times A. So this H times A is the volume of this object. So volume of the object multiplied by the density of the fluid would be the volume of the fluid that would normally be filling up the space multiplied by G is basically the weight of the fluid. So therefore we reach Archimedes' principle. The magnitude of the buoyant force on an object is equal to the weight of the fluid displaced by the object. So normally there would be a fluid in this volume and its weight would be rho fluid GHA, and that is the buoyant force. So we can say that the buoyant force is rho fluid G times the volume displaced by the object, or mass of the fluid displaced by the object multiplied by G, which is the weight of the fluid displaced by the cube. All right. So this actually has an important application. If you think about fish, they swim by regulating their air-filled swim bladder so that they change their volume and therefore control the buoyant force. So if you regulate the air-filled swim bladder, that is going to modulate the buoyant force that you feel, and the fish can swim easily by doing so. All right. Now we have two cases. When we put an object inside a fluid, it may sink or it may float. Now, if we look at the net force acting on an object when the density of the object is less than the density of the fluid. So we have the buoyant force, which is the weight of the fluid displaced by the object, and then we have the gravitational force, which is the weight of the object. So weight of the fluid displaced by the object will have a larger value here because they have the same volume. It's basically determined by the density. So this means that the object will float. If the density of the object is greater than the density of the fluid, the buoyant force will be compensated by the gravitational force on the object, and therefore it will be greater than the buoyant force, and this object will start sinking. It will accelerate downward. Okay, so the buoyant force is the weight of the fluid displaced, raw fluid GV object. The gravitational force is mass of the object multiplied by gravitational acceleration, which is the density of the object, volume of the object times g. So the net force pointing up is GV object raw fluid, buoyant force, minus GV object raw object, weight of the object. And if this net force is positive, that means raw fluid is greater than raw object, the object will accelerate upward, it will float. If the densities are equal, the net force is zero, that's equilibrium. If it was at rest, it stays at rest. If it was moving at constant velocity, it will keep moving at constant velocity. If the density of the object is greater than the density of the fluid, this means this force is negative in minus j hat direction. It will accelerate downward, therefore it will sink. Now, when the object has a density less than the density of the fluid, the object will float. And at what distance from the bottom surface of the object will it stop on the surface of the fluid? Well, that means we have equilibrium. The buoyant force is equal to the gravitational force. So the buoyant force was raw fluid GV displaced. The gravitational force was raw object GV object. So we're going to have the displaced weight of the fluid that is decreasing as the object goes upward beyond the surface of the fluid. And at the point when B is equal to Fg, it will stop, so it will be in equilibrium. All right, so at equilibrium, buoyant force is equal to Fg, so we will have raw fluid V displaced is equal to raw object V object. So when the ratio, the displaced fluid volume divided by the V object, or that is the volume of the object under the fluid, divided by the total volume of the object, is equal to the ratio of the densities raw object divided by raw fluid. So that is basically when we establish equilibrium for a floating object. Okay, let's look at an example. So here is an example. Eureka! Archimedes supposedly was asked to determine whether a crown made for the king consisted of pure gold. According to legend, he solved this problem by weighing the crown first in air and then in water. Suppose the scale read 7.84 newtons when the crown was in air and 6.84 newtons when it was in water. What should Archimedes have told the king? And density of gold is 19.3 10 to 3 kilograms per meter cube. Okay, so here is the first setup. We have a scale that reads the weight of the crown in air, and the weight that we read in air is 7.84 newtons. Now it's immersed into water and the scale reads a different weight. Why? Because we have the buoyant force that is decreasing the reading. So we have the weight measured in water is equal to 6.84 newtons. So if I call this axis the y-axis, the net force on the y-axis is my tension on the string T2, which is what I'm reading, plus the buoyant force minus the weight of the object. And this is equal to 0 because the crown is at equilibrium inside the water. So we see that the buoyant force should be equal to the true weight minus the second tension reading. So we have the first tension reading, T1, was the true weight, 7.84. The second reading is 6.84. So we conclude that the buoyant force is 1.00 newtons. And we know Archimedes' principle, buoyant force is equal to the weight of the fluid displaced by the object. So it's the density of the water, gravitational acceleration, multiplied with the volume of the object. Now, what is the density of the crown? It is the mass of the crown divided by the weight of the crown. Mass, the volume of the crown, mass divided by volume. So this gives us volume of the crown is equal to mass of the crown divided by the density of the crown. And if it is gold, it would be 19.3 10 to 3. And if I multiply top and bottom with G, this would be the weight of the crown divided by the density of the crown times G. And this is going to be equal to the volume of the crown. Now you can see that the volume of the crown is buoyant force divided by density. So volume of the object is basically here volume of the crown, which is the buoyant force divided by density of water times G. So this must be equal to the buoyant force divided by density of water times G. So if I look at this equation, I see that these two G's will disappear and I will be left with density of the crown equals the density of water, mass of the crown times G divided by the buoyant force. Now what is mass of the crown times G? That's the true weight of the crown that was measured in the air. The density of water is 1000 kilograms per meter cube times 7.84 divided by 1 newtons, and we obtain the density of the crown to be 7.84 times 10 to 3 kilograms per meter cube. All right, so now Archimedes reaches a conclusion. If you compare the density of the crown that we have obtained with the density of gold, it's clearly less than the density of gold. So since the density of the crown is less than density of the gold, the conclusion is that the crown is not pure gold. All right. So Archimedes reaches this conclusion. Another example, a Titanic surprise. An iceberg floating in seawater is extremely dangerous because most of the ice is below the surface. This hidden ice can damage a ship that is still a considerable distance from the visible ice. What fraction of the iceberg lies below the water level? So you can see, and that's the reason why Titanic sank. The density of ice is 917 kilograms per meter cube. Density of seawater is 1030 kilograms per meter cube. So the ice is a floating object, right? So for a floating object, we know that we have equilibrium situation. The buoyant force is compensating for the gravitational force. So what is the buoyant force? It's the weight of the seawater displaced by the object, Archimedes' principle, rho SW, G V displaced, and this must be equal to mass of the ice times G, which is density of the ice, G multiplied by the total volume of the ice. So this basically gives us the following result, because we have these two G's disappearing here. So this G disappear. So we find that the volume displaced, V displaced, which is the volume underneath the water, divided by the total volume of the ice, is equal to the ratio of the density of the ice. So we have this equal to the density of the ice divided by density of seawater. So if we plug in the numbers, density of the ice is 917 kilograms per meter cube. Density of seawater is 1030. This is basically 0.89. Okay, so what fraction of the iceberg lies below the water level? This is the volume below the water level. This is the total volume. So that's basically the answer we're looking for. 0.89 is the fraction of the ice below the water level. So let's state this result. The visible fraction of the ice is 11%, 89% inside the seawater. Okay, so that's basically our conclusion. Now, in this lecture, we have talked about buoyant force and Archimedes principle. When we have an object that is immersed in a fluid, it feels an upward force, that's called the buoyant force. And this upward force stems from the fact that we have a pressure differential when we compare the top and bottom surfaces. And these two pressures are linked by the variation of pressure with depth. P top plus rho fluid GH is equal to P bottom. So this pressure difference, basically when we calculate it, using the variation of pressure with depth, we see that is equal to the weight of the fluid displaced by this object. It's the density of the fluid, G, multiplied by the volume of the object, which is the volume this fluid would fill if the object were not there. So that's the volume displaced by this object. So this is equal to the weight of the fluid displaced by the object, which is called Archimedes principle. So Archimedes principle tells us that the buoyant force is the weight of the fluid displaced by the object. And a good application we see in fish, they swim by regulating their air-filled swim bladder in order to control the volume and therefore the buoyant force. Now we have two cases for a totally submerged object. If the density of the object is less than the density of the fluid, we have the buoyant force greater than the weight of the object accelerates upward. If the density object is greater than the density of the fluid, gravitational force is greater than the buoyant force, the object accelerates downward. If they are equal, then we have equilibrium. The object will move with constant speed or it will be at rest. If the object accelerates upward, we will see that when the object comes out of the fluid level, the buoyant force will start decreasing because the volume displaced by the object, that is the volume of the object underneath the fluid, will be decreasing. And when the buoyant force exactly balances the weight of the object, we will have equilibrium. So this situation tells us that rho fluid GV displaced is equal to rho object GV object, or rho fluid GV object inside the fluid is equal to rho object GV total volume of the object. And this equation of the two forces gives us V displaced divided by V object is rho object divided by rho fluid. or volume inside the fluid divided by total volume is the ratio of density of the object to density of the fluid for a floating object. The first example we have seen was regarding a legend. Archimedes was asked to determine if a crown was pure gold or not, which he did using a spring scale. So scale reading, basically first in air we see the true weight of the crown, and then we immerse it into water and we see a different tension here because of the buoyant force. He measures a 1 Newton buoyant force inside the water, and using Archimedes' principle, the buoyant force is equal to the weight of the object, the weight of the fluid displaced by the object, and we comparing the density of the crown with the density of gold from this, because we have basically equilibrium established for this crown inside the water. The buoyant force is equal to the weight of the crown. This gives us a density 7.84 10 to 3, which is less than that of gold. So he determines that this is not pure gold. And second, for a floating object, we see that if an ice floats in seawater, we see only 11% of the ice outside, 89% is hidden inside the seawater, which can easily damage a ship that may not notice the ice under the water. So using the equilibrium condition, buoyant force balances the gravitational force, the weight of the ice. We see that the rho SW, seawater density, multiplied by G multiplied by the volume of seawater displaced by the ice underneath the seawater equals the total weight of the ice, mass of ice times G. We see that the ratio of the volume underneath the seawater to total volume is 0.89, so 89% inside seawater, 11% is the visible fraction.